All right, so the homework that you have on your plate right now is due on September the 11th. Upload that before 8 o'clock on Tuesday the 11th. Last time when we were working through in-class exercise number 5, we didn't quite get it all the way finished. So we're going to begin today's class by completing that. We had already talked about the first page, and we talked about some of the information having to do with the bond table from the second page. So now let's go through that problem number 6, which is on the third page there, and I'll give you a few minutes to read over it, give you a couple of hints, and then after you've got some time to work and collaborate with your classmates, we'll go over the solution. All right, so let's just, let me interrupt for just a moment, and we'll talk about some of the elements of this question number 6. All right, so you receive $50,000 in 7 years. Even if it doesn't specifically ask for it, it's often a good idea to begin with a cash flow diagram. So we've got a 7-year horizon starting at 0, 1, 2, 3, 4, 5, 6, 7. You receive the money, so that means that's going to be an inflow to you. So thus we draw the line up. That's in the future, so we label it F, and the amount is $50,000. All right, so that's in year 7. What is the present value of that future payment? So notice the way that it's asking that, it's not saying how much do you have to deposit in order to have those funds available in the future, but it's saying how much would it be worth today in equivalent dollars? Instead of getting that same money in year 7, how much would you have to receive now for it to be equal? So I'm going to, in this one, also draw the line upward above the horizontal axis there. And so now this is P equals question mark. So this is a really important point. Remember, we talked about early in the semester the idea of perspective, and how sometimes problems are from the perspective of the lender, sometimes problems are from the perspective of the borrower. Well, now in this case, when it comes to the cash flow diagram, what this is illustrating is that sometimes when you are discounting amounts into the past, you know, when you're taking some future amount in year 7 and you're moving it backwards in time, that amount is going to be smaller. But the question is here, if you're using I equals 8%, what is that present value? So if I said you can have $50,000 in 7 years, what's the equivalent amount to take today? All right, so part A says summarize this problem in the form of question/question. And remember, you were quizzed on this. The thing you have to remember is it's find something / given something. And so here what we're saying is, for part A, find P given F. So P/F is the standard way of summarizing that. And we'll put this in parentheses because another way of summarizing this is not just P/F, but also comma I equals 8%. So now we've defined the interest rate, and then N equals 7, because that's the total number of years in this problem that we're going to be taking the future amount back to the present. Any questions about this part A? How we should say P/F, I equals 8%, N equals 7? Okay, now in this list, are some formulas that you can use to solve the problem. And what you need to do is look at either where it says converts to f given p. No, that's not us because we're not given p. We're given f. So converts to p given f. And that does describe what we've got. We have future as a given. We want to convert the future amount to the present. And if we double check this symbol notation, it says p/f. And that does match what we came up with in part A. So what it tells us for here in part B is that the formula is going to be p divided by f is equal to 1 plus I to the negative n power. Okay, write the formula that you could use to calculate your own factor. All right, and then part C says let's actually use that formula to calculate the factor. So the factor is the right-hand side of the equation. You just substitute in the I that we're working with, substitute the n that we're working with. Okay, so what that means is our formula that we're going to use to solve this, p divided by f is 1.08 to the minus 7 power. All right, so take out your calculator, and remember that a key important point of this is when we're doing problems like these, leave all of the digits in your calculator. Don't round off. Keep all of the precision so that we can be accurate to the nearest penny when we use this formula later. So 1.08 to the power of negative 7. Okay. So what we should get is 0.58349, and it continues. So did anybody else get the same value, 0.58349 and so on? All right. So we got the factor that way. D, solve the problem using the factor you computed. And we're calling this the equation method. When we calculate our own factor with I, with n, and then taking into account, which of these symbol combinations gives us the right formula. All right, so part D says, let's find out what is the present value. So if we rearrange algebraically the left-hand side of this equation, we just leave p is equal to f times our factor of 0.58349 and all the rest of those digits. Okay, so the future amount was 50,000. And if you multiply that factor by 50,000, then we're going to get what the equivalent present value of that amount is. All right, so let's multiply that by 50,000. $29,174.52. Okay, so the way to think about that is that if someone offered you $29,174 today, you could put it into the bank at 8%, and it would be equal to $50,000 after 7 years, as there was annual compounding. So any questions about either the cash flow diagram or questions about how we calculated this number or questions about what this number means? So this was the equation method. So the last part of this in-class exercise problem says solve the problem using the factor from the table lookup method. All right, so here's a table, this 8% table, and you always have to be really careful that you're using the right table. On an exam, I maybe would give you a sheet that has 4 or 5 different interest rate tables, and so you'd need to use the right one, otherwise your answer is going to be way off. Okay, so yes, check. We're using the 8% table. Now we need to find the right column, and so we, remember, are doing P/F. find P given F. So we find the P slash F column here, present worth, and we go down to the row that says n equals 7. So here on the left side you can see the 7. Okay, and if we go over, the factor that it gives us is 0.5835. That's really close to what we had before, but it's just they don't have an infinite amount of space in the table, so they have to round off a little bit. So what they're saying is P divided by F is 0.5835. So if we use that to solve our problem, if we put the 50,000 in for the future amount and multiply it by that factor of 0.5835, we're going to get close to our earlier value, but not exactly the same, because here in the factor table there's only 1, 2, 3, 4 digits. So that means our answer isn't going to be accurate to the nearest penny. And we can still express our answer to the nearest penny, but it's not going to be accurate in the same way that the equation method was. So try that. 0.5835 multiplied by 50,000. And the value we get is 29,175. Okay, so, depending on the level of precision your analysis requires, sometimes if you're just doing like a broad estimate, the factor tables are perfectly acceptable and their precision is just fine. Here, 29,175 is pretty close to 29,174 and 52 cents. That's a pretty good representation. Okay, so what we've been talking about is ways to move the timing of money. In this example that's still on the whiteboard here, we were moving money from the future to the present. In this cash flow diagram that's up on the screen, what this shows is you're converting an annual series to a present amount. Now, we've talked about this before, but the key elements of finding the present value when you're given an annual series is that the annual series has to be continuous. There can't be any gap. It has to be the same amount every year. And then one other thing is that when you're converting it to the P, it's the year before the first annual amount. So here we're calling year 0 where we're finding the present, but the first annual payment isn't until year 1. So that if there was also an amount in year 0, then we'd have to add that separately from the conversion we did with the annual series. So here you can see find P given A means that you're going to look up the factor or calculate the factor for P slash A and then multiply it by the annual amount. And that's how you find P. Or there can be the situation where you know the present amount and you're trying to find out what's the annual equivalent. There's a product called an annuity, and maybe your parents are getting to the age where they're starting to think about retirement and where all the money is going to come from during retirement. One of the kinds of things that you can go out and buy is a product that you give a lump sum to either like a bank or an insurance company or an investment company. You give them one big amount and then they guarantee you a monthly payment for the rest of your life. So for people who live a really long life, they end up doing really well in something like that. And some people will buy an annuity and then die the next year and they didn't quite get their money's worth. And so what the annuity product is taking into account is like they have to have an understanding on average of how long people live and probabilities of lifespan. And then they also have to understand the time value of money. But what this is, you can think of this as you're making a lump sum payment and then doing some withdrawal. Another illustration of a situation in real life that's similar to this kind of a problem is buying a business. You might have an opportunity in the future to become a partner in a company where you have to have a down payment of some sort to gain partnership status. Or if you're purchasing a small business, you'll make a lump sum payment, and the idea is that you'll have regular income because of that investment. So it would be kind of the reverse. It would be A slash P. Find A given P based on the interest rate and based on the number of periods. When you move money backward in time, that's called discounting. When you move money forward in time, that's called compounding. Compounding because the amounts get bigger, discounting because the amounts get smaller when you move it back in time. Any questions about this slide? All right, so let's just do a quick illustration here. If you believe that making some modification to a treatment process is going to earn the company $5,000 a year, how much can you afford now to get that extra $5,000 a year? So here's an illustration. How much can you afford to pay now to get an extra $5,000 a year for 5 years if the interest rate is 10%? So you'll notice I should have made some of these options so that you can trick people. It's 5,000 times 5. So people who don't know about the time value of money are going to say the present equivalent is 25,000 because you've got 5,000 and there's 5 of them. But of course we know it's not that because the amount's going to be less because we're moving money that's in the future to the present. Those amounts have to be discounted. So the way that we calculate this is the A is 5,000. We multiply it by the factor for P slash A. So anytime you see these notations, you should translate it in your mind so it becomes second nature. P slash A means find P given A. And then verify. Is that what we have? Yes, we have A. We want to find P. So the P slash A factor, if we go to the 10% table, you'd look it up and it's 3.7908. So that means the present amount you can afford to spend now is $18,000. Do you have a question? No? I know, I was joking. Anytime somebody itches, I try and, do you got a question? Just hoping somebody's going to ask a question one of these days. All right. So here's another illustration. What if you're trying to find the future equivalent of an annual series? Now this is a little bit weird because remember when it came to the present value, it was the year before the first annual amount. Well, they decided, I don't know who they is, but the way it works with find F is that the future value is in the same year as the last annual payment. That's just our standard notation, that's our standard assumption, is that if you're converting it to a single future amount, that timing of that single future amount is in the same year as the last annual series. So here you can see it's an annual series where the first time there's a payment, we call that year 1. And what we want to do is find out if you were taking all of these, maybe this is an annual, like an allowance from your parents. Every year they give you money for tuition and books, but then they want all of it back in a single lump payment after 5 years. How much is the amount? Well, this is find F given A. So F slash A is the factor table we're going to use for this one. So we could go to whatever the interest rate table is, whether it's 7%, 8%, or whatever. F slash A, find the interest rate. The number of years here is 5 because we have 5 years and there's 1, 2, 3, 4, 5 payments in total. And it's just kind of the reverse of this. If you're given an F and you're finding A, the given F is in the same year as the last annual amount. You kind of just have, there's a certain number of these rules that you have to remember. That's one of them that's a little bit weird and awkward. And there's another one that I'm going to show you today that having to do with gradients that's also a little bit weird. But I mean, there's a certain logic to it. I mean, that future amount has to be at some point, and what they're saying is it's in the same year as the last annual amount. So here's an illustration that demonstrates how we can do F slash A. So what if you do something that's going to save your company $10,000 per year? So remember, if you save money that used to be spent, you can count that as revenue. Like kind of the baseline was that we were spending a certain amount of money, so anything you can do to bring costs down is the same as making new money. Okay, so that's, when we look at the cash flow diagram, that's going to be inflow of $10,000 per year. So don't be thrown off by the word save. Sometimes people see the word save and they think, oh, you're saving money in a bank, so you're making a deposit. But that's not what it is. You have to look for those context-specific clues. And here it is that you're saving money that used to be spent. So that's revenue. Interest rate of 8% per year. How much will the savings amount to in 7 years? And this is another one where someone who isn't thinking about the time value of money could be thrown off. They're saying, how much does it amount to in 7 years? That just means add up 7 payments of $10,000. But what this problem is really getting at is what's the equivalent future value of those $10,000 payments. Okay, so here's the cash flow diagram. And actually, that cash flow diagram's wrong because these are revenues. So I'm going to have to remember to, well, I guess I could fix it right now. It's a little bit tedious. These are revenues, and the equivalent in year 7 is also a revenue, because we're trying to find out if instead of all of these small savings, you're taking it as a single amount at one time, how much is it worth? All right, I like that better. What's the equivalent amount on the 8%? Need to move that out of the way. All right, so this is F/A at 8%, 7 years. We can go to the table, find that it's 8.9, so it's equivalent to 89,228. And the reason why the equivalent amount is more is that this payment that they received in year 1, it's compounding over time. So like if you received this payment in year 1, it's as though you put it in a bank account and you earned interest at 8% for 1, 2, 3, 4, 5, 6 years to get it to year 7. And the same thing with this single payment of $10,000 in year 2 is you got it and then you invested it at 8%, and so it's going to be continuing to compound. And so the amounts get bigger anytime you move them to the future. So what we're doing is we're moving this arrow to the future, and we're moving it so many years in the future that it's going to get bigger. This 10,000 in year 6, it doesn't grow as much because it only had 1 year to compound before we got it to year 7. Okay, so the approach then is just to find the table for find F given A, multiply it by the A amount of 10,000, and so it's worth 89,000. Any questions about this illustration? Okay, now this is the one where I said it's also a little bit weird, and they're called gradients. And a gradient is where the amount increases by a fixed value every period. And so a gradient, the line just keeps getting larger and larger and larger with each passing period by the amount of g. And what's tricky about it is you have to remember that in year 1, it's 0g. Okay, so we've got time 0 is the present. And what we're saying is, you know, what if we had to pay increasingly bigger payments every year? Like in the first year we didn't have to pay anything because that's 0g. But then in year 2 we paid a certain amount, g. Year 3 is double that. Year 4, 3g, and so on for as many years as we've got. So that's called an arithmetic gradient. And of course the factor follows the same format where you've got the unknown that you're trying to find and the given amount. And so this is an illustration if you were going to find the present value of a gradient. And so the tricky thing that sometimes students forget is that year 1 is 0g. So actually you don't see the first incremental amount until the second year, the end of the second year. All right, before I turn you loose on the in-class exercise, I wanted to refresh your memory about a concept of linear interpolation. And this is something I know that you went over in 103 and probably other classes as well. But this is a formula that if you are given the 2 points and you want to find the value of a point in between them, then taking into account the slope of the line and how far between those values on the x-axis, you can find the equivalent value on the y-axis. So let's just say, for instance, that you've got between 5 and 7 on the x-axis, and you want to, and this is the input data, so this is the independent variable. On the vertical axis is the dependent variable. So if you wanted to find out what's the equivalent y when you've got x is 6, then we'd start off with the starting value for y, so 12, and then the y1 minus y0, and so that is the distance between the top value and the bottom value, because what we're trying to do is find the slope. And just as a refresher of how to use this, I'm going to leave this slide up when we go through the in-class exercise today, because the first question I'm going to ask you to do is use linear interpolation. And the reason why is that sometimes you won't have the factor value for the interest rate that you want. So it's an estimation, but you can do linear interpolation to find the correct factor, well, at least close to the right factor, for interest rate amounts other than what you have tables for. So this first in-class exercise problem that we're going to look at today, the interest rate that I want to know the factor for is 8.3%, but we only have it for 8 and 9. So you'll be able to use this method to find out what's the equivalent factor for 8.3% interest. All right, so let me hand out the in-class exercise. And so what you should get when you do the linear interpolation is that the interpolated factor for 8.3% is 2.22145. So if you look at the values that are given, it's closer to 8 than to 9, right? The 8% factor is 2.15, the 9% factor 2.36. So 8.3% is going to be somewhere between the two, but closer to the 8% factor than the 9% factor. All right, so what we're doing is we're looking at the difference in the factors and how much that difference in factors is due to the difference in percentages. So my approach was, I'm saying, here's the difference in the factors, the difference in percentage, so the slope of that line in terms of how much factor changes per percent. And what we're doing is we're starting with the 8% factor, and it's going to increase from there because the 9% factor is larger. So with the baseline of the 8% factor and then some amount larger. And how much larger? Well, 0.3 times the slope. So you can get the estimated solution by interpolation, but if we substitute that value into the equation method, then you'd get that the ratio of f to p is 2.22197. So this is more accurate than interpolation because it's not actually linear. The response, because of compounding, the response is slightly nonlinear. I'll give you a moment to copy that down or finish your calculations if you're still working on it. Okay, let's see if everybody's on the same track for this problem too. Okay, the first thing that you needed to do is write the years on the cash flow diagram. So that's easy enough. What we see on the cash flow diagram is that we're starting off with year 0. Wait for it. All right. Year 0 is the present. Year 1, there's nothing there because it's 0G. Year 2, we see 200. Now this is a gradient because it always increases by the same amount. And so you can see year 2 is 200, year 3 is 400, year 4 is 600. That means that G is 200. So we've labeled the years, and we also found out that G is 200. So if we use the table factors to find the present value of this gradient, it will be 930.02. Since this particular table doesn't have a column for f/g, if we want to know the equivalent amount for all of this in year 4, the formula is a little bit more complicated. So we have to substitute in 0.08 for I, N is 4. The factor you should get for that is 6.3264. So if you multiply 200 by that factor, you get it's 1265.28. Anybody else get that same amount? Good. All right. I'll leave that solution up in case anybody wants to continue to look at it or make some notes. Question 3 in the handout says that we're trying to find the present value of this cash flow diagram, but there is a gradient here and an annual series, and they're both on top of each other. So what you're going to have to do is identify what are those two parts. And let me draw an equivalent cash flow diagram on the whiteboard just to show you, because the cash flow diagrams can be pretty helpful sometimes in seeing what's going on. So we've got one cash flow diagram where we're going 0 through 5, 1, 2, 3, 4, 5, and the annual series is that there's always 400. So we've got A equals 400, and we're trying to find out the present value of that. Now on top of that is another cash flow diagram where we see nothing in year 1, but in year 2 there's 30, then 60, 90, 120, so 30, 60, 90, 120. So in this case, we can see that G equals 30 in this cash flow diagram. So you can split apart the given cash flow diagram into its two components and then find the present value of each of the components, and then that's going to be the present value of the whole. So this cash flow diagram kind of tells you what the strategy is. We've got 12%, and you're going to have to use the equation formulas for this one because I haven't given you the factor table. So using the formulas on the first page and 12% interest, what's the present value of the annual series? Then what's the present value of the gradient? And sum the two. So again, what we have to do on number 3 is break this cash flow diagram up into its two parts, into the annual series part and into the gradient part. And that gradient formula is, I don't know, it's the nastiest of all of them there. So I guess once we've conquered it the one time manually, then we'll use the computer and factor tables for the rest of the time. But I just think it's important to at least once have the experience of trying to calculate the factor for the P/G. So let me take a picture of this and I'll bring it up on Cam Scanner. All right, so here's the two parts of it. Here's the find the present value of the annual series component. So that's, if we break this problem down into the expression inside the brackets there, P/A, find P given A, 12% interest and N equals 5. And then we go to the formula table here. We need to find the P/A equation. Here's that P/A equation. And we're going to make the substitution of 0.12 for I and 5 for N. So that's what I've done here, is 0.12 for I, N is 5. That factor of P/A turns out to be 3.60477 and so on. All right, so then if you make the substitution, later on we'll make the substitution where we multiply the annual amount of 400 times that factor, and we find that the present equivalent of the annual 400 amount is $1,400, $14.41 and 91 cents. Now the gradient component of that, we see that there's no amount in year 1 because that's 0G, and then G is in year 2, 2G is in year 3, and so on. So the summary here, find P given G, and here's the equation for it. And if we make the substitutions where 0.12 is I and N equals 5, here's the process of making those substitutions and kind of calculating the intermediate quantities and finding the value of each of the terms. So the factor ultimately is about 6.3970. So that means if we're discounting that gradient to the present, we need to use the factor 6.3970 and multiply that by the value of the gradient, 30. And so the gradient component is a relatively small share of the overall value of that cash flow, 191.91. So the overall sum of the present value of the two components is $1,633 and 82 cents. Any questions about breaking problems into the components? You'll see a lot more of situations like this where there's an annual series that's somehow interrupted by a single amount, and so what you can do is you can break off that single amount to just an individual future value, and then it keeps the rest of your annual series constant. And so you'll just make these small additions or deletions to a complicated cash flow diagram to break it up into pieces that makes it easier to solve. It's much simpler to calculate just two components here than to discount these individual amounts 5 times. All right, so just keeping an eye on the time, I think we probably had better leave it there for now. I don't think we'd have enough time to get to problems 4 or 5. So we will continue those ideas in class next Tuesday, the unknown rate and unknown N. So hold on to the in-class exercise. We'll continue that. Let's, before you go, take one last look at the announcements here. All right, the assignment that you have on your plate, assignment number 4, that's due by 8 a.m. on Tuesday the 11th. So we won't see each other between now and then unless you come to my office hours, and you're very welcome to stop by my office. I'm happy to help you. If you have questions and you want to send me an email, that's also fine. I'll do my best to respond, but let me make a special request. Sometimes, like over the weekend, I might be up in Mineral Wells at a cross-country meet. I won't take my textbook or my solutions with me, But if you take a picture of the problem you're working on with your phone and maybe take a picture of your solution and you email that to me, then that'll give me like a basis to answer your question. Because sometimes I'll be in the middle of nowhere and I'll get a question like, what should we use as the interest rate on problem 7? I don't have the book with me. I don't remember anything about problem 7. But if you send me a little bit more background information, then I can help interpret the problem for you. Or if you just can't be, you're working on it, but you're stuck somewhere. So the point is try and give me as much information as possible, and that might enable me to answer your question earlier than if I have to wait till I can get into the office and get a hold of my textbook to give you that specific info. All right, so that's it for today. Have a good one. I'll see you next Tuesday.